I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, and I'm a professor of material science and engineering right here in Salt Lake City, Utah, at the University of Utah, in fact, in the material science and engineering department. And today, so Andrew's off home with family, and he's left me here alone, but no worries. I have a guest joining me. I'm joined by Jake Baer. Jake, tell me about yourself.
Yeah, thanks for having me. I am a professor, an assistant professor in mechanical engineering at Oklahoma State University. I actually got my degree in material science as well, so I do most of my research in materials related fields, and mechanical is just the department that they have here. I have expertise in a lot of computational modeling and some microstructure evolution, a little bit of experimental stuff, EBSD, SEM. But today, the main focus of my research is phase field modeling, which is kind of a microscale level model. But I've been here for 5.5 years. I guess I don't know if you want any personal information or anything, but that's my kind of career information. I spent a few years at a national lab at Pacific Northwest National Lab before I became a professor.
Killing.
Yeah.
So today we want to talk about phase field modeling. I mean, a bunch of listeners have asked about this. Andrew worked in the nuclear sector for a while before he came to grad school, where he was using tools like Moose. Maybe some of our listeners have heard of these. So we're going to dive into what exactly phase field is. Why should material scientists care about it? What can it do? What can it not do? Maybe get us started. Give us an introduction at the very basic level, remembering that our listeners may be totally unfamiliar with any of this. Like, what is phase field modeling?
Yeah, so basically what phase field modeling does is it makes a transition that's a smooth transition between two different phases of a material. And that can be something like solid and liquid. That can be something like two different solids that are combined into a single material. That can be, the simplest way one of the neat ways that I actually teach this is if you think about having a cup of chocolate milk and you blow bubbles in your chocolate milk, those bubbles will coarsen over time, and you'll get the big bubbles that'll eat up the little bubbles, right? And then you can phase field model that with something that basically makes it so that the surface of the bubble, is a gradient. So it smoothly transitions from one bubble A, to bubble B. And so that's actually something that we use for things like grain growth in materials, which is one of the applications that I do a lot of work in. And you can think about just making some sort of a mathematical smooth transition between two different things that are happening in a material.
Okay.
So that you can watch how they evolve over time.
Awesome. So it can account for multiple phases, and beyond that, it can account for, say, the size or the curvature. What about things like impurities, dislocations, things like that? Does it also, is that too granular or?
No, it can do all that kind of thing. It can have, so with like an impurity or something, what you'll have is you can model a concentration field in a phase field model, and that concentration field can have something related to it. Let's say you're looking at the diffusion of, say, carbon into a steel, right? So you got a low carbon steel, you're putting some carbon into it. You can actually make a stress that occurs in the material as the carbon moves through it, and that'll just be, it's a smooth stress instead of a granular, like atomistic one. It's not an individual atom causing stress, rather it's a concentration of atoms creating a stress.
Oh, very cool.
So there is that possibility for even that low level, but it's done at a more micro scale level.
So why do we call it phase field modeling? This is just thermodynamics. It sounds like that to me anyways. This is essentially thermodynamic modeling, right?
It really is. It's actually the concentration one in particular is a very slight modification of Fick's second law of diffusion. Most people that are listening probably don't know what that is, but it really is a combination of thermodynamics and kinetics. The reason it's called a phase field is that a lot of thermodynamic models will basically explicitly model in distinct phases, and the other type of model at this scale is called a sharp interface model. And so if you have phase A and then a rigid straight line and then phase B, then you have a sharp interface model, and that is still a thermodynamic model, but it's a little more difficult mathematically sometimes because you have to know exactly where that interface is all the time. Whereas with a phase field model, that smooth transition allows a smooth movement of that boundary between phases. So we're able to watch a dendrite grow, right, in a solid, which is, for those people maybe not as familiar with that, a dendrite is the kind of tree-like thing, think of a snowflake, right? Where people have seen snowflakes, they grow in this, they have these branches coming off. So you can actually model the growth of a snowflake with a phase field model without knowing beforehand where that interface starts, where it goes. It'll do it all for you. Whereas with a sharp interface model, every time it moves, you have to redo your math everywhere so that it knows where the boundary is, and your thermodynamics are different in Snowflake and outside of Snowflake.
Gotcha. So the math behind, the math of thermodynamics has been around for quite a while, right? But this is now a computer software that's allowing us to do these calculations to, say, see a microstructure evolve under temperature gradients or stresses or whatever. Therefore, it can't be that old, right? Because computer modeling isn't really that old. Give me the timeline.
Yeah, so this is actually, to me, I'm always really impressed by some of the people that came up with these ideas, because they did come up with them when there really weren't computers. And so you're like, what were they doing this on? But, but the original, the Cahn-Hilliard equation is kind of the first one that came out, and it is developed by two scientists, John Cahn and John Hilliard. In 1958, they have a paper that came out, which is incredible to me because, again, you're not going to be able to model anything with the computers at that time. Like,
it's pure math. This is just pure math treatment.
And so now I think it's a lot more intuitive. We can see what it does. We can see how it's getting more and more useful, obviously, as computers get better and better. But at the time, these guys were just, real pioneers in the area. And they actually based it off of a lot of thoughts that were kind of happening at the atomistic level. And so they don't explicitly talk about atomistics, but you can, if you look at the science that's happening at the time, you can say these were probably a lot of thoughts that were kind of maybe not directly citing, but were around and people were thinking about them. And so, for example, there was a lot of work being done on random motion of atoms jumping between different phases at the time, looking at atomistic different things, looking at migration barriers, energy barriers that prevent one phase from going to another. There was a lot of work being done in the 30s and 40s and early 50s in that area, where you're looking at thermodynamics and kinetics from an atomistic point. And so Cahn and Hilliard, if I were to guess, were familiar with a lot of these things, and then they came up with basically a continuum model, a continuum math equation that they couldn't run finite element simulations to any significant degree with this, but they came up with the math for the continuum equation, basically.
That's so cool. So phase field then sits, it's not an atomistic model. It's not finite element. It's sort of in between these two in terms of length scales that it models. Am I getting that right?
Yeah. So typically we're talking of a length scale between, say, nanometers all the way up to sometimes millimeters. And it just a lot of that depends on the thermodynamics and kinetics involved. The smaller the thing you're looking at, probably the smaller the length scale. So if you're modeling crack propagation, which is one thing that you can model with phase field, that's a really typically an atomistic level thing. So you're probably looking at, thousands of nanometers, so in a few microns at most. But when you're modeling other things, if you're modeling diffusion or if you're modeling corrosion rates or things like that, then you can get to a much larger scale. Then you can look at, say, millimeters. And the time scales are also much different, where with like atomistic simulations, typically we're talking in time frames that don't really make sense to anybody, like picoseconds. Right?
Corrosion might take years.
Yeah, right. Yeah, and you're doing a simulation where you're even like, it's funny to me when we do stress simulations in atomistics. I do them sometimes, but you do a stress simulation. You're like, what if I apply a stress of 500 megapascals in 3 picoseconds? And you're like, is this even like this is ballistics?
Now, what experiment would ever achieve that?
This is ballistics now. It's no longer like a normal stress test. But anyway, the time scales for phase field go from a few seconds up to, I've actually done some with corrosion a little bit that have modeled days, right? Or year. You can even with some corrosion models I've seen that go like years.
Further out, huh?
Yeah. And so that, again, that depends on the kinetics. A really slow kinetic means you can do bigger time steps typically. And, but there's a pretty broad range. And it is usually the solving of a phase field model is done through finite element methods. Okay. So you can do finite element, or you can do finite difference, or finite volume. Those are kind of the methods that people typically use to solve phase field models. So I don't want to say it's not those things. It's just an application of those things at a smaller scale than people typically think of.
Okay. So I'm not an expert in any of this. So maybe our listeners aren't either. Let me explain the difference, right? Finite element, finite difference, finite volume. When would you know how to use the different one of these for phase field? Like, is there what's guiding your thought process when you're selecting which method to use to model some sort of microstructure evolution in materials?
So there's probably a lot of people that think about this a lot more than me. I typically go with whatever my software is that I'm using does, right?
Whatever's on the back end, don't think about it.
Yeah, right. No, I would never claim to be a computer scientist or a programmer. I do that as much as I have to, absolutely, and then I try and avoid it.
I see. So when it comes to phase field, you're like you're not a method developer. You're a use the tools for some interesting application person.
Mostly. I've developed some methods, but they've basically been, I have to have this method to get what I want done, so I'm going to develop it. And outside of that, I'm not completely unfamiliar and incapable with it, but I do try and avoid, I'm not a huge fan of coding and programming, which is funny because I do all my work in coding. So the main differences are, like, I use Moose. That's what I use almost exclusively. Moose is a finite element solver. That's it. And so the differences are, finite element solver basically breaks a material up into elements, little tiny pieces. If you have a square, you cut it into a grid of squares, right?
And these are not elements, atoms. This is just a group of atoms.
Just a group,
and it's not even like a grain. It's smaller than a grain,
right? Yeah. So they can vary in size dramatically. So you can have as small as less than a nanometer, or you can have as big as probably the biggest I've ever seen, which doesn't mean it's the biggest out there. The biggest I've ever seen was several microns in size.
Okay.
And so it's possible to have a wide variety. And again, this all depends on the length scale and the thermo and the kinetics involved in the specific problem that you're trying to solve. But these can be large groups of a material, and it's not really tied. It's basically how much resolution do you want, right?
Sure. Okay. So you break your material up into these chunks of atoms, all equal shaped, equal size, that are connected to one another.
Maybe. They don't have to be.
Not even necessarily. Interesting.
Yeah, so they can be the same size. They can be different sizes. Actually, a lot of the simulations that I do have what's called an adaptive mesh, where the mesh is really small at the interface.
Yeah,
so
that makes sense.
I'm looking at a grain
crack,
boundary.
Right?
Right, like a crack.
There you want the resolution, but in the middle of the grain, you don't care. It's not changing very much.
Yeah, so at the crack tip, I'll have
Oh, cool.
less than a nanometer grid size, but as you get further and further away, that grid size gets much bigger. And that
That makes
saves a
sense.
ton of computation time. So you're able to do much bigger simulations. It's a lot easier to do like 3D, especially if you're doing 3D simulations of materials. You really need to save as much computational power as you can, right? Um, but they can be different sizes, but they can also be different shapes. So there's things like tetragonal meshing, which makes like a whole bunch of different shaped triangular prisms and puts them all together. And that, I mean, I don't really understand how they put that together. But basically, at each point of every element, whether it's a 2D square or whether it's a 3D cube or a tetragonal prism, each point is called a node. And you basically have a smooth transition of your value, say concentration or phase variable. You have a smooth transition between each node, each point on each element. And so over time, each node point, each tip of your element communicates with all the elements around it. And I don't know how familiar people are with atomistics, but I actually like to explain this as, they probably aren't. I like to explain this as atomistics. If you have a bunch of ping pong balls and they're all in a box, right? You can say that the ping pong ball is affected directly by each of its closest neighbor ping pong balls, right? All the ones that are touching it, if you push them, they will push it.
Okay.
But if you touch it, it doesn't necessarily have an effect on a ping pong ball that's a foot away, right? And so the same thing you could say, each element point affects its neighboring element points. But as you get further away, that effect is diminished. And in finite element, it's zero. If you're not directly connected with it, there is no effect directly. Now, if I touch a ping pong ball over here and it touches a string of ping pong balls, it can affect it, but it's all indirect. It's one space at a time, right? So that's how I think an easy way to think about kind of how those elements go together. It's basically if I have 100 elements in a row, it's 100 math problems, each one in a chain.
Okay. And so by solving these sort of simultaneously or iteratively is how you model then the overall microstructure evolution for whatever the process is you care about.
Exactly. And so each of these is solved. It's kind of a mathematical guess and check. Iteratively means that you have a guess answer. It checks that if you put all these values in for all of these elements, how much error do I have in the math?
Oh, interesting. So it's an
Right.
optimization? Really?
It is optimization. And so basically, the math starts with some big error and it says, well, that was bad. How do I adjust these values to get closer to zero
Yeah,
error?
what must the microstructure actually be to lower my
Right.
residual a little bit?
Yeah, and so you're watching the residuals, you set your tolerances, you say, okay, if the total residual gets below, 10 to the minus 6, I'm happy, or whatever.
Okay.
Those can vary pretty broadly as well, the tolerances. I've even seen some tolerances as bad as like 10 to the minus 2, so you're like a full percent off, maybe. But in
Interesting.
engineering, we don't care about a percent off, right? Like,
Yeah.
sometimes.
Okay, so this is cool. I see then why this is a useful tool because, microstructure evolution drives so many things that we care about as engineers. You've got a bunch listed here, additive manufacturing, like the grain structure or defects, right? Obviously, the as manufactured structure is usually not very good. They will oftentimes hip it or do different things to sort of evolve that structure to make it better. In batteries, there's dendrite growth, right? That's a huge problem that impacts the degradation of these batteries. Magnetic materials, there's these domain walls, right? As you make a hard magnet, right? As you do polling, for example, when you apply a magnetic field as it goes through its Curie temperature, right? All these things, these are all things that you can model then with phase field, which is pretty rad.
Yeah, and one of the really great things actually about it is it's really easy to couple in a lot of these different physics. Because you have that smooth continuous gradient and you have different things, you can do magnetism really easy. You can do radiation really easy. You can do electric fields. All of those things can have a big effect on microstructure. They can have a big effect on processing, and they can have a big effect on material properties as like a final product material. So
Cool. So you mentioned that one of the packages that you use almost exclusively is Moose. I assume there's others out there, though.
Yeah, there's actually quite a lot of them. So a lot of this originally was done by individuals in like C++ on their computer, or you can actually do a simple phase field model in like Python or MATLAB if you know what you're doing. But the ones that are typically used are like Moose, which is what I use. There's one called Prism that a lot of people use that are very well known in the field. I think that was developed at Northwestern University. There's PhyPy, there's OpenPhase, there's COMSOL. So those are just a few. And then there's actually still a lot of people in the world that do their own custom solver where they write their own C++ code or something like that. So
Are
there's
all of
no
these are these open? Are these closed? Like, do you pay for these?
some of them. So Moose is open source and it is freely available. It was developed at Idaho National Laboratory. So the reason I use Moose is because I worked at Idaho National Laboratory during my PhD. They actually
Yeah, was this Michael Tonks? Did he create it, or is he
yes.
just like a user of it? Because I
He's
know
a
he talks about it a
very
lot.
early user of it. Michael Tonks was, I would say, very important to the development of it. He's not one of the people that is like listed as the original developers, but he's definitely, he was
That's
there
cool.
when it was first developed. I think let's see, Derek Gaston or something like that is one of the like first minds behind
Cool.
it. But there's and it's been a while since I could get the names wrong, but there's a large group at Idaho National Lab. The other ones, some of them are open sourced, and I think Prism is. I think a couple of them are. ComSol is definitely not. So some of them are open source. Some of them cost a lot of money. Obviously, doing your own custom solver is free, but yeah.
So I'm an editor at Integrating Materials Manufacturing Innovation. Awesome journal, by the way. And we get a lot of submissions having to do with phase field. So I'm seeing it all over the place. One of the things I see a lot of right now is ways to improve the efficiency of phase field through changing the way that they parameterize it, right? You're basically, as I understand it, you're fitting, in some cases, you're fitting, right, your observed system to thermodynamic equations. And the way that you can do that is various, right? Because there's different parameters that you could choose. So we'll see that. I'm seeing integration with machine learning. I'm seeing parallelization via GPU utilization. Like, it seems like there's a lot happening in this field right now. You want to talk about that?
Yeah, so a lot of those things are very important because we're trying to get to model bigger and bigger systems, more complex systems, different physics being brought in. And so a lot of the ways to make that happen is to improve how efficient your computation is. So with a GPU, you can do a much more, it's a lot easier to get a lot more parallel processing if you have a GPU capable solver, right? And so because GPUs, you can get a lot more processes going. I don't actually understand exactly how GPUs work, but I know that they're basically able to give you an order of magnitude more computation power if you can set up your solver to work with them. Outside of GPUs, there's also things like Fourier transforms. And so there's different mathematical methods for making the math quicker to solve. And so one of those is like Fourier transforms, turning your variables into non-dimensional parameters. They actually use those types of things a lot for things like fluid dynamics. But also in phase field, there's several groups that use Fourier transforms to basically simplify the math so that they can do larger system.
Cool. So I'm guessing that anytime you do that sort of thing, we see the same trade-off in DFT or molecular dynamics, that there's always a resolution or precision versus efficiency trade-off to be had. Sounds like that's also present in phase field.
Yeah, and I think this is actually true of all computational modeling. There's one of my favorite quotes about computational models comes from a guy named George Box. He was a statistician, and he said, and I'm going to paraphrase this, but he said basically that all models are wrong.
Yeah.
And because all models are wrong, it is important to understand how they are wrong, because it is silly to be chasing mice when there are tigers abroad.
Interesting. I've never heard that version. I always heard that all models are wrong, but some are useful variant.
He does say that too. So there's a couple of different places where he said a similar quote, but I like the one about mice and tigers just because I think it's cool. funny visualization of someone
Yeah.
being like, well, there's mice in here, and somebody else saying, well, there's a freaking tiger right there. Like,
So let's wrap up the episode talking about some applications. Like, why are material scientists so keen on this technique? Like, what's the big deal? Like, why use it over finite element method? Why use it over molecular dynamics? Like, why is this such an important field?
so it's really the bridge, right? You need, so from atomistic to go clear to continuum, and when we typically think of continuum, we're thinking of modeling like a full part of something. Well, phase field modeling and other similar models, people may like things like sharp interface models like the kinetic Monte Carlo or things like that, Potts models. These are all things that bridge the gap between atomistic and full-scale continuum. And this is important because a lot of the actual, in material science, we're always interested in the structure, property, and processing relationship. They have that three-pointed triangle of structures, properties, and processing methods. The phase field modeling, basically, you can think of, it gives us a way to look at structures and how these three things relate in a more applicable manner. So structure, property, and processing, how those all relate. With a molecular dynamics simulation, you're never going to model, for example, a continuous cast strip of some metal, right? Because it's just too long of a time scale. It's far too large. But what you can do, or friction stir welding, or like any other processing method that you can think of, you just can't do it with an atomistic simulation. With phase field modeling, what you can do is you can take continuum level models also can't do it with enough information about how the structure is changing, right? You can model maybe thermal property, like what is happening to a temperature of a material as it's continuously cast. Or you can model things that are bigger like that, temperature or stress fields. But you can't understand how those are affecting the microstructure, which determines the final properties of a material. So what I can do is I can take a sample of the material, say a cube of steel that's being strip cast. I can take the history of stresses that I got from a continuum model. I know that it undergoes these stresses as it's being pushed through the thing. I know that it has this temperature profile, so it's slowly decreasing. It goes up in temperature, then it decreases in temperature over time. Then I can take, from atomistic models, I can take how those interfaces that we just talked about that are all important, how those create a barrier to growth or to different things like that, how impurities prevent grain growth, right? And so I inform the model with properties from an atomistic model. I inform it with conditions from a continuum model. And with that, I'm able to predict potentially a very close microstructure to what we actually see in the material. And then I can predict from that microstructure, how will that affect the material properties? How will, say, if I have impurities and they're all 10 nanometer particles, how will that make a different microstructure from if they're 50 nanometer particles?
Yeah, that makes sense. So this, as you're describing it, what comes to mind is the whole field of digital twins, right? And for our listeners who aren't familiar, like take like a jet engine, right? Like you've got a turbine engine, which is made of these components, right? And we know that those are going to evolve over time, right? There's heat cycles, there's stress, there's all these things happening, there's corrosion, and it's inconvenient or maybe impossible to remove those components and test them, but we need to know what they're doing over their lifetime because they will fail at some point. So if you can't have the physical model, then what's been put forward is this notion of a digital twin of the real material where, okay, you characterized it at its fabrication, so you know what its grain size was, either the exact, right? Technically, I've seen people do like exact grain reconstructions, or maybe have like a statistical representation of it. And then what you're saying is that you could use tools, including finite element, to model how that material might be evolving over time and then forecasting, say, failure events or whatever, so that you don't actually have those failure events on your physical sample because you did it on this digital twin instead.
Yeah, so you can say we expect it to fail at this point, and then you apply some safety factor, right? You say, okay, well,
Sure.
then we're going to take it out a month early or something just to be safe or whatever. And those can be very broadly safety factors. But yeah, that is essentially what we're trying to do is we're trying to make a model that can give us, say, a safety factor for failure or a prediction, or can give us an optimized processing method for creating the longest lasting process. Like if I want to run 1,000 different tests of strip casting, that is expensive and requires all the materials. It requires the setup. If I want to run 1,000 different simulations of it, I just have to have a supercomputer, right? Which is super cheap. I get the model working, and then I just run a series of simulations, and it requires almost no man time. It requires no equipment. It requires no materials outside of the computer. So it's a way to do materials design. It's a way to develop new processing methods. It's a way to do safety checks for fracture or for failure. And that's really the goal, is to have all of these modeling methods communicate with each other to address the tigers in the room so that we can get an ideal
Yeah, I love it.
prediction.
So question for you is, are there like some killer case studies that you could point to? Like what's a materials, problem or some new material that was discovered or something? Like what's the thing that you point to as like, dang, this is like the cool thing that phase field made possible? Or is it just like involved in so many things, but behind the scenes that it's sort of the unsung hero that we just sort of take for granted, but it really is enabling? Can you point to one versus the other?
It's hard to. I would say it's hard to say that there's a lot of things where it's like, yeah, phase field did this by itself, because I really think a lot of these methods work together.
They all complement
right?
each other for
They
sure.
all complement each other. They all create a complete picture. However, there are a lot of things. Let's see. I'm trying to think of a specific one that would be
the best like success story of phase field modeling. I mean, Moose, for example, I know that, Andrew, when he was working in the nuclear sector, there's just a lot of these processes that experimentally are pretty brutal to try and actually do. Irradiated environments, like these are experimentally dangerous or hard or expensive. And so being able to do experiments there in silico, right, via computation, become really, really valuable. I think he pointed to a few of those.
Yeah, that's a great example. One example is like Michael Tonks's work. You brought up Michael Tonks earlier. Michael Tonks has done a lot of work in like uranium gas bubble formation, right? So over time, as a uranium fuel rod is in use in a nuclear power reactor, as fission is happening, it creates these gas bubbles in the material, which as they grow, they gain in pressure, because every time you think of a void that is surrounded by a hard metal, and as that void gets bigger because of the neutron irradiation and all this stuff going on, smashing elements, things that are happening, basically the bubble gets bigger and it creates a high pressure environment, and eventually that explodes.
What gas is forming? Is it like the volatilized metal? Is it oxygen from the oxide? Like what's actually forming?
Boy, I don't remember I've learned this before. I think it is oxygen and other stuff, but I don't remember well enough to tell you.
Okay.
It's probably
that's the
a
type
lot
of problem that phase field could actually forecast and sort of predict.
And it actually has. Like I said, Mike Tonks has done a ton of work in that area.
That's cool.
And so there's a lot. And then when those bubbles explode, right, you're trying to hold this uranium thing in basically a tiny pipe that's like a millimeter thick or something. They're really thin pipes. And so that can be a big problem. That's nuclear is a great example because, like you said, it is very expensive to do nuclear experiments.
Yeah. Well, all right. So, Jake, my last question for you is, what did we not cover? Anything else you want to say about phase field modeling to people? If they never hear about it again, what's their takeaway?
I will offer a couple of things. There is a NIST, the National Institute of
Standards and Technology.
Standards and Technologies. Yeah. So the NIST has a website called Phase Field Hub, that actually has really great images of some of the phase field modeling that has been done by people all over the world. If you want to see some examples of simulations that people have done and just look at some cool pictures.
This is rad. I'm on it right now. These are really cool pictures.
Yeah, so there's some really great pictures. A lot of them you can click on them and it'll take you to the like research group that did that picture, and they'll have new ones. They'll have even more. So that's a really great resource for just seeing the types of things that people have done in the field recently and that are just great to look at. So, and I can share the link with, or you found it, I guess we can.
Yeah, we'll put that in the show notes for sure. This is really cool.
So that's a really great resource for just seeing some of the neat things that are being done. Outside of that, I think that it's just fun to realize, like, I think that a lot of normal people have a hard time grasping atomistics. And I would say this for myself, right? Like when people talk about molecular dynamics, when I was starting graduate school, I was like, atoms are too small. My brain doesn't go that far, right? Like, but if you talk to me about something that is a smooth transition between things, I can think about that, right? I can think about hills and valleys. I can think about how I tell people materials are lazy, right? Materials want to be in the lowest energy state. They want to be at the bottom of the lowest hill. And so I can understand that just from a conceptual level. And so for me, phase field modeling is a very approachable mathematical thing for your average person, right? It's not now, I don't expect your average person to go and run a bunch of simulations of this, but I think conceptually it's easier to understand. So that's one neat thing for me about it. Other than that, I think, we had a pretty good base of stuff covered. So,
cool.
Yeah.
Well, thanks for joining us, Jake. We appreciate it. We love getting the expertise of people that do things that we don't. It's fun to learn a little bit today. I'm going to remind our listeners that the Materialism podcast is sponsored by a couple sponsors. We have Materials Today. We are grateful for our sponsors at Materials Today. That's an excellent journal by Severe. It's more than just a journal, though. It's a whole research community they have put together. So special thanks to them for sponsoring the episode.
Today's episode is sponsored by California Nanotechnologies, or CalNano. And I just want to point out that there is a really cool opportunity coming up. One of the coolest parts of this podcast is we get to sit down with experts and just pepper them with questions. It's awesome. And it's really fun to have sort of immediate feedback from them. And we think that this is something that our listeners would probably really like to do as well. Well, you can't obviously be on the podcast with us. You can talk to experts by attending conferences and trade shows. And one of those is coming up. It's the TMS 2026 spring meeting in San Diego this year. CalNano is taking advantage of the fact that that meeting in San Diego is just up the road from where they're at. And so they're going to use this close proximity to offer an SPS user meeting / workshop. It's taking place directly after TMS, so you can just double dip on your trip, take one trip out to California and attend both meetings. You can see the itinerary if you go to www.calnanocorp.com/SPS workshop. I think you're going to see a lot of really cool opportunities there to learn more about SPS from the experts. Hope I'll see you there. Hey, we want to remind our listeners that today's episode is sponsored by Momentum Transfer. I've said it before, but having access to synchrotron data for powder X-ray diffraction is an absolute game changer. The resolution and intensity allows you to access information about your materials that are just not accessible with lab X-ray. And now with this company, you can get access to that synchrotron data without time-consuming proposals, waiting for them to get approved, sending somebody to go actually do the measurements. It's an absolute game changer. I love their business model. I hope you'll take advantage of it. And they've made it possible. In fact, if you go to momentum-transfer.com and you sign up, then you'll be able to get total scattering and PXRD measurements for 5 samples for free. You just can't beat that. So check them out.
And then lastly, thanks to the people that make the music for the show. Thanks for the listeners who reach out and suggest episodes like today's on Phase Field. You can get a hold of us. We are materialism.podcast@gmail.com or the @materialism.podcast on Instagram or pretty much wherever else. We would love to hear what you want to hear next. So drop a comment, whether this is on Spotify or on YouTube or wherever you're listening to this. leave a comment. I try and get to all of those. Send us a message on Instagram. We try and respond to everything because we appreciate our listeners. We love that you're out there. And with that said, we will wrap it up and we'll see you in the new year. See you, everybody.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.